Hey guys, welcome to the first video in the second channel. I've decided to make a second channel exclusively for math and science videos and technical videos, just to reduce the clutter in the main channel. The main channel is only for fun content, and there will be main channel videos coming as well. That's when, because I've had a 4-year gap, the moment I can think of good ideas, there'll be videos on the main channel as well. So today we're going to be looking at an interesting property in circles and triangles, and it's that the orthocenter of a triangle, if you were to take its reflection with any of its sides, it's going to fall onto the circumcircle of the triangle. And that is a very interesting property in triangles, because it seems to connect triangles to circles in this really pretty way. Because who would have thought, if you were to take the image of the orthocenter, it's going to fall onto this other mathematical thing called the circumcircle. So very interesting geometric property, and we're going to prove this today. We're going to see how it's gonna work. So I'm just going to start by drawing the orthocenter of this triangle, and if you guys need a refresher, then the orthocenter would be the intersection of the orthogonals of a triangle. So let me just go and drop the perpendiculars, and that looks 90 enough. Okay, and the last line is just going to be passing through this intersection. Alright, so all of them look 90 enough, but of course they may not be 90, it's not drawn to exact scale. And so here I have it. Here's my orthocenter, and I'm going to call this H. So the theorem, or the property, says that if you were to take its reflection, that is, if you were to reflect this orthocenter with respect to this line here, then you're going to find that the orthocenter is going to lie on the circumcircle. So it's just gonna reflect and fall somewhere over here. I think I'm eyeballing it again. So here's the orthocenter. You took its reflection, it's going to fall on the circumcircle. This is what we have to prove. Why? And my first thought when it came to proving this was that I'm basically sharing my proof, because I think it's pretty intuitive. So my first thought was that if this is sort of like a piece of paper, right? And so you can think of it as being folded. So the piece of this triangle here, let's give us names. So here is A, B, C, I guess, right? And that point can just be H. So AHC is like this whole triangle, this whole piece of paper is A, B, C, and then H, but H is folded onto that. And so if you were to unfold it, then you would get something like this. Okay, I'm just going to draw it in red, leave the dotted lines. You would get something like this, where the orthocenter is supposed to be, right? And if you would unfold it, you would get something like that, and this H would fall over here, which for the time being I'll call it D. And so if you can prove that ABCD is a cyclic quadrilateral, then you're done, because if that's a cyclic quadrilateral, H would have to be on the circumcenter. And so you're done proving, because the act of reflecting is sort of like folding it over. So you've unfolded it, and by unfolding it, you have shown that you've gotten a cyclic quadrilateral. And by showing that you've gotten a cyclic quadrilateral, you've shown that the orthocenter has effectively traveled to the circumcircle. So how are we going to prove this? And cyclic quadrilaterals have this property where if you take the opposite angles and then you sum them, you get 180 pi basically. So that's what we're going to use. We're going to give names to this triangle. We're going to the triangle's angles. We're going to call okay, so I'll call this one alpha, and we can call this one maybe it's better to use red so you can see. So we'll call this one alpha, then we'll call this one delta, then we'll call this one beta, and we'll call this one sigma, and the top one can be called gamma, and this one you can call it theta. So right, so in a cyclic quadrilateral, once let's say if I've opened it, so this angle would basically be alpha plus delta, right? Because when you open it, this is going to be delta as well. Same for this. When you open this up, this part is going to be sigma. So the opposite angles are basically alpha plus delta and beta plus sigma. So alpha plus delta plus beta plus sigma has to be pi, right? And then we have that gamma plus theta, because once you unfold it again, you're gonna get something like this, and this would be theta. So we have to show that this is a cyclic quadrilateral, right? And this whole thing is a cyclic quadrilateral, something like that. I don't know. Wait, let me just join this up. So it's not really touching the circle. That's probably because drawing errors, but as long as we have the math to prove it, that would be enough. So alpha plus delta plus beta plus sigma. Beta plus sigma should be pi, and gamma plus theta should be pi. Okay. Put that in red. So this is what we have to prove. Okay. So if you looked closely into the triangle, then we can call this E and we can call this F. So take a look at triangle AEC, and you can use your usual triangle properties, and we know that this should be 90, this should be 90, and this should be 90, and it makes sense because the only thing unique to these orthocenters is that they come from these altitudes. And if it's not for this altitude, if it's not for the orthocenter, you could have used this argument for any triangle in any circle. So obviously it doesn't work that way. So a good guess would be to work from this altitudes. So if you look at triangle AEC, then you can make the deduction that beta plus delta should be pi over 2, because the third angle in this triangle is 90 degrees, right? And similarly for AFC, you could also make the same argument again and say that alpha plus sigma is pi over 2. And as you can see, that concludes the proof. We're done, basically. We're done proving this fact. So it follows very simply if you just think about it. This really pretty property, this adds up to pi, and we're done proving the first one. And the second one need not be proved, because as we know, in a quadrilateral the angle sum has to be 2 pi, 360, and if we have proved that 2 sets is pi, then the other set is obviously going to add up to pi. So that's done. We're done proving it. So since A, B, C, and H make, shouldn't actually say H. Let's call this H prime, the one that's fallen over onto the circumcircle. H prime make a cyclic quadrilateral. It must be that the orthocenter's reflection is lying on the circumcircle. So this section of the video is for those people who are curious about why the opposite angles of a cyclic quadrilateral has to add up to pi, and the answer to that is what I'm going to try to give. And a cyclic quadrilateral is basically a quadrilateral that can be inscribed onto a circle. Okay, and the moment you have a quadrilateral like that, it's gonna follow from a couple arguments that the opposite angle is going to add up to pi. So to show that, you just have to draw the diagonals on into the quadrilateral, and from then it's just inscribed angle theorem. So the inscribed angle theorem says that if you have a circle and there's a chord to the circle, then no matter where you draw it, so basically the chord is going to subtend an equal angle everywhere. So this would be theta as well, and this would be theta as well. And if you were to compare it with the center of the circle, then the arc would be of 2 theta, something like that. All right, so here's obviously the center of the circle, which we probably wouldn't be needing, but I'm going to add it in anyways. Okay, so let's start naming things. If this was alpha, then this would be alpha as well. Right, so if this was alpha, this would be alpha as well. And if this was beta, then this would be beta as well. Alright, and if go on, you just got to go on naming it like that. So what else is an angle that we've left? Alright, so if this one was gamma, then that one would be gamma as well, and we're left with one last angle, this one. If that was delta, and this one would be delta as well. So we've basically used inscribed angle theorem for every chord. Okay, and we know that the angle sum will be 180. 360. So we have alpha plus gamma plus delta, and that's going to be pi. I've basically done the division by 2. Okay, and there we go, we have it, because as you can see, alpha plus beta plus gamma plus delta, pi. And we have here gamma plus beta and alpha plus delta, pi. There you have it. So pretty interesting properties coming out from really simple geometry.